This is lecture number 11 in this course on electric machine design. In this lecture, we are going to solve some problems related to transformer design, and we are going to use the equations and expressions that we have been using in the past few lectures. So I would suggest you to first take a look at these questions without seeing the solutions, and try these questions on your own, and then if you are able to do them, you can check how I do them, or if alternatively you want to check the way I solve it first, you can do that as well. So the first question we have today is we are given a three-phase 50 hertz oil cooled core type transformer with the following dimensions. The distance between core centers is 0.2 meters. The height of the window is 0.24 meters. The circumscribing circle has a diameter of 0.14 meters, and the flux density is given to be 1.25 Weber per meter square. The current density delta is 2.5 ampere per mm square. The window space factor is 0.2. The core area factor is 0.56. And you are also given that the core is two-stepped, so you have to estimate the kVA of the transformer. Okay, so these dimensions are given. So what should we do? How do we proceed from here? We can start by first mentioning what is given to us. Just summarize what is given to us. F is given to be 50 hertz. The flux density is 1.25 Weber per meter square. The spacing between the core centers is 0.2 meters. Current density is 2.5 ampere per mm square. Height of the window is 0.24. Window space factor Kw is 0.2. The diameter of the circumscribing circle small d is 0.14 meter, and the net iron area, or the core area, is given to be 0.56 d squared. Okay, since this is the factor, core area factor is 0.56, so the iron area is going to be 0.56 times d square. Okay, so let's begin by first calculating the net iron area, AI. That is given by 0.56 d squared. So d is given to us to be 0.14, so AI comes out to be equal to 0.0109 meter square. So AI is given, AI is calculated. Next, we know for a core type transformer, the distance between the core centers is given by this diameter of the circumscribing circle plus the width of the window. So the width of the window can be calculated as this. So substituting these values, this is 0.06 meters. This is number 2 that we calculate. Now area of the window AW is equal to HW into WW, and on substituting these values you get it to be equal to 0.0144 meter square. Okay, now all of these parameters we have with us. What is to be done? We have to put them in the equation, the output equation for the transformer. It's the three-phase core type transformer. So we know that the output equation, output kVA, is given by the expression 3.33 times F BM delta kW AW AI into 10 to the power minus 3, right? So we have to substitute these values, and on substituting, what do we get? 3.33 times 50 times 1.25 times 0.01009 times 0.2 times 0.0144 times 2.5 into 10 to the power 6 into 10 to the power minus 3. So important thing to note here is that this is current density, and current density originally is given in ampere per mm square. So you have to convert, so that there is uniformity in units, you have to convert this area, ampere per mm square, into ampere per meter square. So that's why it gets multiplied by 10 to the power 6. So the kVA Q comes out to be equal to 16.33 kVA. So this is the kVA of the transformer that we have been asked to design. Fairly simple, this question. You just have to put the values that we have in the equations that are already known to us, and this question is solved. We now move to another question where we have a single phase core type transformer. Let me mention this here. And some ratios are given to us. What are these ratios? We are given that the ratio of the core height to the distance between the core centers is 2.8. We are given that this small d to capital D is 0.56, and the ratio of the net iron area AI to the area of the circumscribing circle is 0.7. The current density is 2.3 ampere per mm square. The window space factor Kw is 0.27. Flux density B is 1.2 Weber per meter square, and the distance between the core centers is 0.4 meter. And of course, you are given that frequency is 50 Hertz. So you have to again calculate Q, or the output kVA. Okay, so let's start. We know that the capital D, that is distance between core centers, distance between core centers, D is equal to 0.4 meter. So also we are given, using this expression here, that core height to distance between core centers is 2.8. So height of the core you can calculate. Is 0.4 into 2.8, so that is 1.12 meter. We also know that dia of circumscribing circle, d small d, is equal to, in this expression it is equal to 0.56 times capital D. So this is equal to 0.224 meter. Okay, Then we know that for single phase core type transformers, the width of the window is related to the two D's as follows. So when you substitute these values, you get 0.176 meter as the width of the window. Now we have to calculate area of the window AW, which is equal to HW into WW. So substituting these values, we get point AW is equal to 0.112 times 0.176. We get 0.197 meters square. The area of the circumscribing circle is pi by 4 d squared. So we already know d square, so this area is going to be 0.0394 meters square. Then we have this ratio, net iron area to the area of circumscribing circle, that is given to us to be equal to 0.7. So net iron area AI is equal to 0.7 times the area of the circumscribing circle, so that is equal to 0.7 times 0.0394. This comes out to be equal to 0.0276 meters square. Now we have to calculate this factor Q, which is the output kVA, and since this is the single phase transformer core type, we know that the Q output power is given by 2.22 FBM delta kW AW AI into 10 to the power minus 3, and again you have to factor in this delta correctly, so it has to be converted into ampere per meter square. So when you put in these values, you get that this Q is equal to 450 kVA. Another straightforward question, no difficulties, should be easy to understand. And finally, we move to the last question for today. It's a fairly long question, so I want you to pay attention to this. You are given a three-phase core type delta to Y transformer. This has to be noted. It is rated at 300 kVA and the voltage ratings are 6600 to 440 volts. It's at 50 Hertz and has three-stepped core, where the diameter of the circumscribing circle, small d, is 0.25 meter. The leg spacing is 0.4 meter. The volts per turn ratio is 8.5 volts. Current density is 2.5 ampere per millimeter square. The window space factor kW is 0.28. The stacking factor Ki is 0.9. What you have to do, you have to estimate the dimensions of the transformer, and you have to also calculate the sizes of the conductors, as in the area of the conductors that have to be used. Okay, so let's start. We know that this is a delta Y transformer, so delta corresponds to 6600 volts and Y corresponds to 440 volts. And we also know that we have this ratio ET, which is the volts per turn. This is given to us. So number of primary turns can be calculated straight away, is equal to 6600 over ET, which is equal to 8.5 volts. So this number of primary turns is 776 for us. Now number of secondary turns is going to be, it's not going to be 440 divided by 8.5 straight away. It is going to be 440 divided by root 3 divided by ET. Why? Because in case of delta, the line voltage is equal to phase voltage, but in case of Y connected transformers, the phase voltage is 1 by root 3 times the line voltage. Sorry, the phase voltage is 1 by root 3 times the line voltage. So you have to calculate this for per phase voltage. So this comes out to be equal to 30. Okay. Next, you will calculate the primary side current. And how do you calculate the primary line current? It is equal to Q times Q divided by root 3 VLP into 10 to the power minus 3. We are interested in the line current here of the primary side. So kVA is 300 and this is root 3 times 6600 times 10 to the power minus 3. So this current is 26.24 amperes. The line current of the secondary is Q times root 3 VLS into 10 to the power minus 3, which when substituted gives us 393.65 amperes. Okay, so from this ILP we can calculate the area of the primary conductor, ILP over delta, which is equal to just a second, this is equal to, sorry, I made a mistake here. Yes, so since this is the phase current, I'm sorry, this value 26.24 is the line current in the primary. So here you have to calculate this area using the phase currents. So I will have to divide this by root 3. So phase current in the primary divided by delta, this is equal to 26.24 divided by root 3 over 2.5, and this is going to come out to be 6.06 mm squared. I will repeat this. We are interested in calculating the line currents first. We will calculate the line currents first, and then we will calculate the phase current. Okay, so this when divided by the current density, this gives us 6.06 mm squared for the primary conductors. And for the secondary case, which is the delta, in the delta case the line and the phase currents are the same, so we'll use this current. So it's going to be IS over delta, so it's going to be 393.65 over 2.5, and this is going to be 157.5 mm squared, the area of the secondary conductors. Now we will then calculate the copper area. In the window AC is equal to 2 TPAP plus TSAS, and when you substitute these values, you get AC equal to 18855.12 mm squared. So from this we can calculate AW, which is AC over KW, which comes out to be 67339.71 mm squared. Then you have the area of the circumscribing circle, which gives you the value 0.049 meters square, where this diameter d, small d, is given to be 0.25 meter. Now also what you have to do, you have to calculate the gross iron area, and here we make an assumption, not an assumption, but we know from the knowledge of multi-stepped cores that this AGI, the gross iron area, is equal to 0.84 times the area of the circumscribing circle. You get this expression while deriving the areas in the core derivation. This is where you get these areas. So when you substitute these values, you get this gross iron area AGI equal to 0.0369 meters squared. Okay, we are given the leg spacing D, it is 0.45 meter, and we also know that this D is equal to width of the window plus a diameter of the circumscribing circle. So the width of the window is capital D minus small d, that is equal to 0.20 meter, and of course height of the window can be calculated using area of the window divided by width of the window, so that comes out to be 0.335 meters. And another important ratio that is given to us, we will whenever this question is asked, whatever the assumptions you have to make, they will be told to you, but some of them you have to think logically. Like for example, the width of the largest stamping A is 0.84 times D. So this is comes out to be 0.21 meter. This again is a derived expression. You can refer to the book for this. Okay, so this is 0.21 meter. Now the overall width of the transformer is W, and it is equal to 2D plus A. So this comes out to be 1.11 meter. The overall height H is equal to HW plus 2HY. So this comes out to be where this HY is equal to A, width of the largest stamping. So we calculate the overall dimensions, the width of the largest stamping, the width of the window, width of the transformer, and height of the transformer. So these three factors were asked from us, and we have been able to calculate these factors. So these were three questions and were fairly simple, nothing difficult. All of the material that has been, all of the questions that were asked have already been discussed in the material for them has been discussed in the class. If at all you feel that something has been left out, you can always refer to the book. And additionally, I would inform you that you should try to solve more questions from the book. You can look at solved examples to get an idea, and you can solve end of chapter problems. In the textbooks rather, which I've already mentioned, to get a better understanding of the subject and practice more so that you are able to solve questions whenever they are asked in the examination, and of course at the end to get a better insight at transformer modeling and design. So with this we come to the end of this lecture. In the next lecture we will talk about some more, I think we will try to find out some more, we'll try to solve some more questions, and then we will talk about the rest of the things that have to be covered in this unit, and then we will close this unit on transformer design. So see you in the next lecture.